Hello and welcome to the part 9 of hexagonal multi-surface pattern lesson in Grasshopper. In previous lesson we finished single surface pattern mapping and in this one we will map the pattern on a BRAP, meaning we will create a pattern across multiple surfaces, which is the main goal of the script. So that's the script we basically finished in the previous session, and I will remind you that you can go into the description to this video and download that, so we will be in the same page. And on top of that there will be another file, it's called serve.stp. This is a new geometry which we'll be using as a test to finish the script and actually map the pattern on a BRAP. So I really encourage you to go in and download that. And when you did this, let's actually import it together into the Rhino and proceed with the script. So in the Rhino series, I will go to the file, import, and I will take this file. As I said, it's in the description, called serve.stp. This is the collection of surfaces. I will click open. And in the prompt, which is called stp import options, this is a step file, I will uncheck join surfaces and hit OK. So here, let me switch, double click to the perspective mode and look at this new collection of surfaces. Now I'll click the first one on the top one and hide it. I will type hide command and look at these two. Now this will be the new set of surfaces which we'll be using to and try to map our current pattern onto this collection. So these are two surfaces, two separate ones. So I'll click here. You're going to see the one is selected. Here is another one selected. So in the previous lessons we worked on a single surface. Today we need to work across multiple ones. Now let's look at that a little bit closer. Now first of all, they are two independent surfaces, and if you look at the shading, it's quite noticeable that the shading is different, right? So, and it doesn't mean that these surfaces are not perfectly flowing. They are continuous. And the problem here, what the nuance is with the importing itself, because when you're importing from the other programs, it can take the slightly different colors and parameters for the tessellation for the different kinds of surfaces. So this is not an issue. The next important thing is, let me actually select them, hold Alt and click and drag to make a duplicate, is the fact that they are not only separate surfaces, but they are trimmed surfaces. So if I'll click this one, drag it away, you're going to see that there is a hole, right? And once again, they are continuous. So all the edges are continuously aligned and they are perfectly matching. But we have a hole here, and the surface, this one, is trimmed as well as this one. So if I click the surface and I will type Untrim All, it will untrim it, and you're going to see that it was originally a rectangular surface. Same here, Untrim All, and you're going to see that this is actually the full surface. So as you're going to see, it is a construction, and it meant to represent something more closer to the real battle scenarios where your model is not a single surface. There are multiple surfaces joined under the different angles, the different directions. They have holes, they have trims, all of this kind of stuff. And we want to take our hexagonal pattern and map it on this construction. So first of all, to understand the problematics, because it's not straightforward, let's actually use our script and try to bring these surfaces in and see what happens if we will plug them into our surface slot. But before we do that, let me actually go in, turn everything on, and with this surface, we will need that later. And I will go in and I will change the tolerances for the document. So this will be our new testing ground, and this is the first time when we actually save it for the future. So this collection will persist in the next lesson as well. So first, let's click on this icon with the cogwheel, and we'll go to the Units tab, and we'll look at the properties. So this is the properties of the documents, and again, it's the document. And as you're going to see, it has a model unit, absolute tolerance, and angle tolerance. And this is basically it in terms of tolerances. If you are from Alias, you probably will be surprised, because in Alias we have a bunch of options here, It's a generalized software. It's much simpler in this regard and has only a few parameters. So absolute tolerance is your position, angle tolerance is your angle deviation, right? So the parameters of the documents are important because Rhino inherits what Rhino has. So whatever tolerances you have, the Grasshopper will follow, right? So I will go in and increase right now the absolute tolerance to 0.001 millimeters and the angular deviation to 0.1 and hit OK. Right now, I will do it later, but for you, I will suggest you to go to the file, hit save, and just save this construction somewhere else where your Grasshopper script file located. Okay. So now let me select this surface and hide it again. We'll talk about the surface later. Select these two surfaces together. Select our input surface, right click, and construct a bridge. Set multiple surfaces like this. All right, let's look at the result. Not ideal. Something is not right. Now remember that our script works perfectly with a single surface, right? We're using mapping command, we did everything here, it all works right. But here, for whatever reason, it's not. What's going on? What's the problem? Now the problem, of course, with the fact that these surfaces are separate surfaces. If I will use, for example, only one surface from this one, let me use the list item, and I will pick only the first one, you're going to see that it works like a charm. No issues. If I will switch this to the next surface and plug that in, no issues. It works like a charm. But together, they do not wanna work. You're gonna see we have this kind of breaking, like the complete shit show. Why? Well, because every single surface is unique. Every single surface has very specific geometric properties, its own basis functions, its own parametric domains, and its own orientation. They are indeed different, and the fact that they are joined together continuously doesn't mean that this is a one object with uniform domain. It is not. There are two, or maybe three, or maybe five, or maybe 50, or maybe more than 100, which is quite a common scenario when it comes to the modeling. Because when you model, you construct your surfaces with multiple different surfaces, right? Different patches, different angles, different trims, and so on and so forth, and they all unique. So the question you might have, okay, can we actually take this construction and basically assign a single domain, the domain which will be true for this surface and for this surface at the same time, right? One big uniform parametric space, because once again, two different parametric spaces, it goes through one, then it goes through the other one, it goes in the different directions, everything breaking. Well, the quick answer for that, no, we can't. This is the nature of NURBS. Every single surface is unique. Every basis function for every surface is unique, and the properties for that is unique. Its directions, its density, its orientation, everything is unique. You can't construct a uniform domain. And trust me, for the last 20 years, a lot of our smart people try to do that, try to change the concept of the NURBS so it will be more friendly to parametric, and they all failed, to be honest. So the previous big hit was T-splines in 2008 when this concept supposed to solve the T-junctions, and it kind of did that, but it now was accepted by the industry for multiple reasons. Today, the new kid on the block is M-splines. The M-splines can give us a really good, interesting features. However, they still can't really change the nature of NURBS, and the domains and parameterization of every single surface will still be different. So actually, the first person who actually, or the team who can solve this, probably will create a new concept of NURBS and probably will get a Nobel Prize for that. So that's out of question. We really can't directly take the surfaces and use its own parametrizations together and create a coherent structure, coherent uniform domain. Currently, it is impossible. But it doesn't mean that the problem is unsolvable. It is indeed solvable, but in a different manner. So there are two options how you're going to approach this to construct a seamless pattern across multiple surfaces. One of them is simulations. It's a really heavy approach, very specific and not really very popular in the industrial design, for multitude of reasons. But there is another one, a more generalized, a more uniform and universal approach, which we use for, well, decades already. And this approach called Approximation Projection. And this is the method I will be teaching, and this is the method actually we will use for our script. We design our script in the with this idea to actually use the approximation projection. Now, what the approximation projection is, let me actually click on this icon to temporarily turn off everything which Grasshopper tries to do, and look at our surfaces. So approximation projection is the method where you construct a pattern on a separate geometry, which is a single surface. It doesn't matter how complex it is. It can be just a plane, it can be very like distorted and curved geometry, doesn't matter. It's supposed to be a single surface. And we use our script, we already did everything, to construct the proper arrangement of points and our proper pattern. And then we project this pattern, these primitive data, I'm talking about the points, or planes, actual planes are very important later, onto our BREP, basically bypassing the fact that we can't rely on parametric space of every individual object of our collection. But for that, we need first a surface which approximates the geometry which we want to get a pattern on, and the second, we need to convert these collections of surfaces in somewhat of a uniform geometric type of data, which actually called, it has a name, it called Polysurface or a BREP. Let's start with the surface first. So here I will turn the original surface back in. You're going to see there is a surface. Yes, it's quite dirty. It has quite a lot of spans. It's not a problem for parametric. Now, this surface is basically sits above the collection of surfaces in question at which I want to have a pattern, and it approximates it. Approximates it because it's not identical. It can't be identical. Imagine that you're modeling, right? And you constructed, I don't know, the some kind of a product, I don't know, a mice, for example, computer mice, right? And you constructed it with 150 different surfaces and patches and so on and so forth. And then you create another surface on top of that and basically represent perfectly all the complexities of your product, right? It's impossible. It doesn't have that amount of freedom. That's why you need so many surfaces in the first place. That's why the method called approximation. We're not trying to perfectly match. We are trying to cover and somewhat match as much as we can. The more accurately we represent the original geometry, the better. Sometimes it's literally impossible, and then you basically create a blob around that. Sometimes it's really possible, and then you try to be as accurate as you can. So imagine that we have the surface. Here it is on top. And once again, this is not perfect. It's not an offset or something. It's just me manually aligning the surfaces to maintain the proper edges, nothing more. All right. So I will create a pattern on this surface, and then we will project it on our collection of surfaces. But as I said, collection of surfaces right now is just a list of individual surfaces, right? So if I look at our imported geometry, you're going to see there are two separate surfaces, right? And this is a big problem because when I will project, it will project on them individually. I wanted it project on them as a whole, as if these two surfaces will become to be a one general geometric block. And for that, we use a concept of polysurfaces or BREPs. And this is in a way the method which takes your different surfaces. They may not be even connected. They can be in the different places, and place a geometric tag on them, a meta tag, which basically tells the system to treat it not as a uniform domain space. Once again, it is impossible, but as a one geometric shape with uniform geometric property, not domains, but just as a geometry. Let me show you how it's done first. So let me select the surface. I will type hide. I will select these two surfaces, and in the Rhino, I will type the command called join. Join. Come on, join. Enter. So First things first, you see shading changes. So the viewport of any CAD system, of course, is a representation of a CAD geometry through meshes. So this is a tessellated geometry, polygons eventually. And all of this shading, is based on the calculation of normals. And now as you're going to see, when I join these surfaces together, I actually have a much different, completely different representation, one single material and the proper normal calculations across of them. And that's a first marker of that become to be a uniform geometrical piece. Now if we'll select it, you're going to see that in the prompt it says one open polysurface added to selection. And when I click on that, you're going to see I can pick it as a whole. So this is a polysurface. And this polysurface term is not the only one which describes this construction, this geometrical construction. The second term will be a BREP, stands for boundary representations. These two terms interchangeable, they literally mean the same thing, and even in the realm or in the span of one ecosystem, it can change. For example, in Rhino, it's called polysurface. But in the Grasshopper, you will not find polysurface. In the Grasshopper, it's called BREP. But once again, this is the same thing. Let us bring BREP into the Grasshopper. So I will go into the parameter section, into the geometry tab, right? We'll know how to bring geometry, how to stream the geometry, and we will look for the BREP. Where it is, here it is, BREP. Let's bring it in. Right click, it's already selected, set one BREP. And if I'll turn that back in, you're going to see that now I have indeed a BREP. It's selectable. Let's look what's inside. Okay, it says referenced BREP. What's inside this reference BREP is two surfaces. They not merged, that's still two different surfaces, but they just will be treated as a one geometrical, not parametrical, geometrical object with base geometrical properties. If I will explode it basically on its components, it will get back to our original surfaces. Now this command in Rhino and Grasshopper has the same name, called explode. And if I'll do that, I'll type explode object, plug that in, plug that into the panel. You're going to see that indeed now we have two different surfaces. It says squares because they are indeed squares. When we deconstructed the object, it already has a meta tag, and it tries to merge them in the one geometric shape. So it has a very specific description here. It's a model surface, it's a square. I mean, yes, but actually they are trimmed surfaces. So if I'll specify, and you know how to do it, this type of geometry is a surfaces, and it will tell me that they are two trimmed surfaces, which indeed they are. So once again, list item, plug that in. This is the surface number one, right? And this one will be the surface number two. So once again, the BREPs or polysurfaces, they can't merge surfaces together with the uniform parametric space. All of them will be independent. Every single one of them has its own domain anyway, right? So in this regard, nothing changes. But the fact that they are as a single geometrical block is very beneficial for projections, because we will not be projecting on individuals, we will be projecting in a one geometric block. Let me just as a metaphor, right? Imagine you have a trash bag, right? And there are a lot of trash inside. I don't know, like broken eggs, like pockets of milk, whatever you throw there, right? Now all the entities there are unique, right? They're different, they have different properties, but together in the bag they have a different property overall. Like that's a bag now, it's a bag with stuff. Well, this is the same thing, this is the bag with stuff, and we will be working with that as a whole. Okay, right, let me delete this now. And as I said, first and foremost, we need to construct a pattern on our temporary surface to project it on our BREP. And actually, I believe I deleted the BREP as well, right? Yes, I did. Well, shame on me. So the BREP is still there. So let's bring this surface. But before we do that, let's actually inspect it. Now, all of this geometry comes from alias. So I made it an alias. I'll export it as a step file and bring it in. And when you do that, a lot of parametrization specific to your surface modeling system will carry through the step file. So, and it can be completely different from what Rhino can do or should do. So the results may be unpredictable. So let's see what's inside and let's look at the surface. Now, first things first, this surface has a lot of spans. This is horrible for surface modeling, but it's absolutely okay for parametric design. For in our case, it's supposed to represent, not being accurate on itself. So let's first check the direction of a surface, because different systems orient surfaces differently. So what I'm going to do is I will type direction, right? It's something we did before, and look at the orientation. You're going to see this white arrow. This white arrow is a normal direction and it goes down. What does it mean? Surface is flipped on itself. This is not a good idea, so we need to push it back. So basically we want that our z direction goes up. What about the x and y? Now, in most cases, in the situations like that, alias, just from experience, flip the u and v orientations, not parametrically, but geometrically. It's not a big issue for us. I will just want you to remind that, because it will be important when it comes to the planes and the orientations of planes. For now, I don't really want to do anything about the u and v directions. I can swap them, but I don't want to. Instead, I will flip the normal direction. So I click flip and hit enter. So now it orients properly. So direction again. So this is the face, the front face. This is the back face, or a side and a b side, right? Okay, that's nice. Now let's reparametrize that. If you watch my previous lessons, you know that we want a very uniform distribution of points across this surface, meaning that the control vertex is supposed to be more or less uniformly distributed. To do that, we rebuild the surface with a lot of spans and 3x3 segments. So select the surface, type rebuild like this. Now my go-to is 40 by 40 in UNV, and the amount of degrees will be 3x3. I'll hit OK. Like this. Now we have a new surface. It's much more uniform and dense. Let me select the original one and hide that, type hide. And here we have our modified surface. What's next? Well, let's actually try to bring it as is and see what happens. So I will click on the surface, input, set one surface, and our script already kicked in. So it's working, no errors, it gives me something. But what it gives me, let's look at this. Well, that's probably not what we want. Let's look at the parameters, and this is a good thing, so that will be on the same page. So our divisions is 28 by 28. We are in anisotropic flat top orientation, right? We are in a U anisotropic orientation as well, which means that they are working together on a U direction. We are in the open type structure. That's logical, it's not a closed geometry. And we are visualizing only hexes, not triangles, not quads. And it's not working properly. You probably already know why. You're going to see how stretched it is, right? Meaning the mapping, the domain is wrong. The domain doesn't represent the actual surface, which is not surprise when it comes from the alias. Let's look at its domain. Okay, so the domain of the surface is, this is the single domain, so I'm sorry, domain squared. So let's look at the squared domain. Oh, sorry, it's already squared domain, my bad. I'm looking at the wrong data, holy shit. So yeah, so the U is from 0 to 1 and V from 0 to 20, right? Which means this is 0 to 1 and this is 0 to 20. And of course, because we have such a huge difference in the aspect ratio, it shrunk, right? You already know the effect. So what we need to do, reparametrize that. What is the actual aspect ratio for this? Well, I can extract isocurves, measure the isocurves, or in the middle, and plug that in the values. But just from look of that, I would say that if I will set that the ratio 1 to 1, like a square, because it's kind of look like so, it will be more or less close to the proper aspect ratio. And that's exactly what I'm going to do. So I'll click on this surface and I will type reparametrize. We already did it before, right? let's look. U domain starts from 0, that's okay, and ends at 1, that's okay. V domain starts from 0, that's okay, and ends with 20, that's not okay. It will be ended to 1, so the ratio will be 1 to 1. Let's hit enter, and for this surface the ratio 1 to 1, because it looks like a square, gives us the proper orientation. Our script kicks in, it does its own compensations, and it tries to maintain the proportions of the hexagons as much as it can. It did a pretty good job, isn't it? So now I will select the surface and hide it, right? Let me just select the B wrap for now and hide it as well. We already imported both of those. So this is our surface, this is our B wrap. And before we do projections, let's look at the pattern on a surface, right? So now as you can see, this is the V direction, and the V direction is expanded. And we already know why, because we are in the anisotropic flat top. It tries to maintain proportions with the same amount of divisions, right? And it pushes itself outside on a V directions because we are aligning on the U direction. So we are aligning on U, V follows. Okay, cool. This is okay. We'll sort that out later. But if I look closer, you're going to see that my hexagons ends where the surface ends. Well, that's great. This is exactly fantastic. However, we don't have hexagons which are falling off, at least one. And because of that, these sections become to be triangles. And even though that if there will be the hexagon and it will be trimmed, it will be a triangle also, but the overall collection here of points is problematic. So that leftovers will not be a part of a hexagons. But in most situations, you really want them actually to be a part of the hexagon, even if it is trimmed. You will understand later why. We, of course, give ourselves an option to change it, and we already have an option to change that, and we can add or remove additional hexagons in the different directions. And this is our plus x and plus y parameters. So plus x relative to u. So let's go in and add additional rows. Capitalize on the power of our script, right? So how many I need? Well, it's 6, so we need to add plus 6, right? 6. Here we go. All right, look at this. Now the ends are still there, right? But we have one extra rows of hexagons. Now we're fully covering our temporary surface. This is a temporary surface with our pattern. Fantastic. Now let's talk about projections. And for that, let me actually toss these B-wrap closer to the end, right? So I will basically like select this, all of that, or maybe even like this, and drag that somewhere here, right? Okay. All right, so that will be our B-wrap. This is our surface. Now, before we move on, I owe you an explanation about these outputs of the node. We already used this node before. I explained how it works, but I postponed explanation of all of these parameters except the point, right? So it is time to do it now. So if you look here, you're going to see that except of the points on the geometry which we used, we have normal, U direction, V direction, and a frame. All of that is very important for us. We will be using like all of them except in U and V directions. So normal and frame, really, really important. Let's talk about that a little bit. So what is normal? Let me visualize that. So normal is a vector. Let's go to the display, the vector display option. So normal is a vector. More specifically, this is a unit curvature vector. The unit curvature vectors called normal vectors. What does it mean, unit vector? Unit vector is a vector with an amplitude of 1 unit. If I will plug the anchor to the point and the vector normal to the vector, I can visualize my vectors. You're going to see they are very small, right? Their length is 1, and they are perpendicular to the surface at a point. Every single one of those, these one and these one and these one, they perpendicular to the surface they were placed on. This node is pretty smart. and it does a lot of calculations. And what's more importantly, it calculates not the normal vector, it calculates a curvature vector. Basically, it calculates our formula, which I explained in the previous lesson, to the second derivative and finds a curvature vector. Now, the curvature vectors are not unitized. They are different in length. Some of them are longer, some of them are shorter. They basically represent the radius of osculating circle, and that's basically the number for the curvature. The bigger the vector, the bigger the curvature of a surface at a point, and the smaller the vector, the smaller the curvature, the smaller the number, all right? The normal vectors are the curvature vectors. You're going to see this curvature vectors of the second derivative, they're always perpendicular at the surface at a point, all the time. That's the nature of that. And the normals, they just take the current vector, whatever amplitude it has, and it's unitize that, making it the value of 1. This is a very standard procedure, and not, by the way, only in NURBS geometry, but in polygonal modeling, even though that the normals calculated slightly differently. But the concept is the same, perpendicular vectors, right? Normals means unitized. The next two vectors are u direction and v direction. They are vectors also, and they are also unitized. So the u direction at every given point shows me the vector which follows in the direction of a u domain, and the v direction in the direction of the v domain. So here we already have actually 3 vectors, right? Normal vector, u vector, and v vector. Fantastic. All right, what's about the frame? Now the frame actually is a plane. What is a plane? Plane is a localized Cartesian coordinate system. What is a Cartesian coordinate system? You already know, right? I'm sorry. It is a 3-axis, right? 3-axis. One of them is like, x, another one is y, and another one is z, right? The main property of the Cartesian coordinate space is we have these vectors perpendicular to each other, 90 degrees all the time. So frame is a plane, a local Cartesian system which has coordinates in the original Cartesian space, which actually placed on a points on a surface and oriented based on the parameters of the surface. That's why it's not called a plane, even though it is a plane. It's called a frame, because it's not just a plane which orients in global x, y, z and just sits there or there or there or there. It's the plane which was already oriented on the surface, which is an amazing, amazing property, trust me. So first of all, let's look inside. What is frame? And guys, I'm talking about that because we really need this. We will be using it in this lesson. It's not just, for your interest. So here we have on the frame very specific description. Origin, and this is the actual point of our frame, and a z vector. This is the representation in the panel. It actually has much more inside. And the z vector is our normal vector, this one. And indeed, if I will look at the normal vector, plug that in, and check it, you will notice that it is the same. It just numbers around it, 0.47, 0.58, 0.66, right? So this is the normal vectors, or the z vector is a normal vector. Now let's look at the planes themselves, how they actually look and what they have inside. So I'll double click and I will specify that this frame is a plane. Please show me the plane, and we'll plug that in, right? And it shows me the plane. Now at this point, your planes may be huge or maybe very small, and you're like, oh my god, I can't see shit. Let's go to the display, preview plane size, and set the value. Mine is set to 4 right now, right? So they're not very big, not very small, right? So this is a plane, or its visual representation, right? Let's look at that a little bit closer. So first of all, right in the face, you have a grid. Now this grid is just for visualization. It's not real, it's fake. But there are 2 very important elements here, the red line and the green line. And I believe you already guessed, they are the axis. They are the axis of your plane, axis of a local Cartesian coordinate space. This is x, this is y, and there's supposed to be a z. It never drawn, but it's there, right? Instead here for the z, you see our normal vectors, right? So if I will inspect the plane, you will notice that it indeed has the same representation as the frame. But if I will deconstruct this plane on components, I will see much more information. Now, to deconstruct the planes, we'll go to the vector plane, deconstruct the plane, this one, because this is a plane. If I'll plug the plane here, you're going to see how many options I have. I have origin, points, x-axis, y-axis, and z-axis. So basically, this stuff, these planes, consists of a point and free axis. And these free axes are not random. They oriented on a surface because they are coming from the frame from this node. Meaning that the z-axis is equal to the perpendicular normal vector. It is the same, right? And the other ones are still have some relationship to the surface. Which one? Now, first of all, as I said, the surfaces are oriented on a surface. They are following the surface. But there is a catch. The surface itself has two different domains, U domain and V domain. So basically two directions. These two directions may not necessarily be perpendicular. The surface can be skewed. V direction goes in like this, and the V directions instead of a perpendicular goes like this, right? This is U and this is V. It is totally possible, right? Our planes are always perpendicular everywhere. So how are these planes aligned? Very simply, it will take the normal vector as a base. This is our first vector. It's always perpendicular at your origin all the time. Then it takes one of the directions. It can be either U or V. In computer graphics, in general, we agreed upon the fact that the U direction is the main direction and U direction relative to X. We already talked about that before. But sometimes, and some systems can flip the geometry for its own purposes, and Alice is one of them. And sometimes it flips them not parametrically, but actually geometrically. It's not really a big issue, but I would just want to mention that it will be either the U direction or the V direction. Depends on which one system treats as a main for the imported geometry, right? And that means that it has two vectors, one of those, only one of those, and we have two vectors, one vector and another vector. How it calculates the third vector? Once again, it may not follow the other direction. Well, it calculates it using the cross product operation. So this is basically a vector multiplication, right? And the cross product always give you a vector which will be perpendicular to the other two. So cross product between two perpendicular vectors give you another perpendicular vector, right? Or maybe not perpendicular vectors, but we'll get another perpendicular vector perpendicular to these two, right? That's how the plane constructs all three axes. Z-axis already normal, the x-axis will be U or V direction, and the y-axis will be a cross product. Or y-axis will be the U and V directions, and the x-axis will follow, right? It depends on your overall orientation of the surface's parametric and geometric space. But in general, U direction is X, normal is Z, and Y will follow using a cross product, right? Let's look what it is here. So if I will specify a part of the normal direction, I will specify the U direction. What is the U direction? U directions go this there. And yet that's another example of importing from LS is that the U direction become to be our Y axis instead of an X axis, and X axis become to be a V direction, right? Not a big deal. We can always rotate it, flip. This is not an issue. We can deal with this. But now at least you understand how it's oriented, right? So two vectors, the third one is a cross product, and it inherits the parameters of curvature and the direction of the real surface, and that's why they flow around the surface, which is extremely important. Now, the general difference between the planes and the points is that the planes not only have the points, but they, as you're going to see, have orientation, which we can change. So whatever geometry we want to place on these points, if we want to, we can orient it relative to the surface. When we have only the point, we can't do it. Meaning that eventually, instead of a patterns of points or lines, we need originally have the pattern of planes. And we will do that. For now, we're still working with points. It's easier this way, but then we will swap them onto the planes. All right, this description out of the way, let's actually talk about the projection. So we need a point. We will be using that. we will need a frame, but a little bit later. So right now I'll just hide that. And I need a normal direction, because when we're projecting, we need to specify the direction, in what direction we're projecting, right? Let me actually show it to you again. In what direction we're projecting? In what direction we'll be projecting every point? We're projecting on the normal direction. But look at the orientation. Orientation goes up, which is okay. It's supposed to be up because the surface is properly aligned. But our BRAP is underneath, meaning that we need to take our vectors and flip them because they're supposed to go down. Now, we will not change the properties of the surface. We will not flip the surface. Surface already oriented properly. We just take its vectors and flip them. Can we do that? Yes. We go to the vectors, vector tab, reverse. This will reverse the vector. So if I'll plug it here and then here, you're going to see that it changes orientation. Now, does amplitude, the actual length, is important for projection? No. It's a raycast in a way. Like, very, very simplified version. So it's not important what's the length. It's important, the direction is what important, okay? So this is the vector, this is our point, and let me right now as well bring them in here. That is my point. We will need them a little bit later as well. And this one will be our vector, okay. That will be our plane, right? So let me just kind of line it like this, like this. Oh my God, come on. Okay, now it's already right. Okay, well, good enough. So now we need to do a projection. We need to take these points and project it on this vector, right? For that, we have two options. Option number one, the ability to work with the BRAPs. This is our BRAP, with the BRAPs directly. It's called BRAP closest point. We talk later about what closest point means, why it's called closest point, and what it actually does. It's a good projection instrument, but not for us, for reasons. We will talk about that later in the future lessons. For now, we will use another one, which is called project point. The project point locates under the point tab in the vector section. Here it is, project point. Now this node does projections as well, but it, instead of a closest point, it specifies the direction. This is the one we're looking for. So the point is our point, the direction is our vector for every given point, and geometry, well, it's whatever you want. A surface, a mesh, a BRAP or polysurface, whatever you want. In our case, we are working with our big bag, right? Our big geometry, which is a collection of two surfaces, and we'll be using that as our geometry, right? So let's do that. Point to point, direction from our vector, let's put it this way. And the geometry will be our BRAP. Let me actually specify that this is a BRAP. So it will be more convenient, I believe, to debug just in case. This is our BRAP, right? And this is our BRAP. Okay, so if you look here, something interesting happened. Let me hide the original points, our original grid, which is on top. Ctrl Q, I'll remind you, and let me remove this one. And look at the points. Look at that. The points were projected from original pool onto the BRAP. And as you're going to see, no issues, no intersections, no problems, because we are not bothering with the parametric space. We are bothering only on the real geometrical representation, where the geometry actually is. And where it is, where it intersects with our projection, here it is a point. Not actually intersects, projects. It's a different concept. And here they are. Fantastic. You must say, well, awesome. Thank you very much. Roll the credits, right? Not quite. Actually, it's not a clean result. And if we look at our point output, basically what we have, oh, look at that. What the hell is this? Let's look closer. Now, first of all, let me just kind of turn the original plane on and talk about the problems. Now, the problem number one, we projected points, but the points which wasn't able to project because there is nothing to project onto just vanished. Poof, disappeared. You may say, well, that's a good idea because we have a lot of leftovers like this. We don't need them anyway, right? Yes, that is correct. But remind you that we add additional rows here to cover our leftovers, and they're gone as well. No more. But they just not projected. But the points here were projected, so we have 3 leftovers now, right? It's going nowhere. We have real 3 leftovers, and another 3 are just kind of missing, right? I can't construct a proper hexagon from it, right? So it's actually not ideal. And if you look here, this is the perfect representation of what I explained. Look at the first hexagon. This is probably this one, right? Look at it. Null, 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 null. What the null means? Null is, it's not a number, it's a string, and more specifically, it is a tag. It's the pretty common tag in programming in general. This is a marker, or as I said, a tag of information which is supposed to be there, but wasn't able to calculate. And it wasn't be able to calculate because there are no surface. We try to project, nothing to project onto, that's a null. So the place for the data is still there, and the null is a placeholder for that. And this is a very important property because we can operate with these nulls, and we will operate with these nulls to reconstruct the parts of the missing elements which we actually need. All right. So this is null, and we don't actually need this one. We don't need that, right? Why we need all the nulls? It's supposed to be cancelled, and this is supposed to be cancelled. Look at this one, 0, 2, 0, 1, which is probably this one. Look at this. It has 2 points missing, right? It's probably these 2. 1 is here. It's probably this one, and then 3 missing again. Do we need this hexagon? Yes, it is. If at least one of those, right, one of the collections in our, because this is a branch with 6 points, which basically gives us an enclosed hexagon, right? If at least one of them is touching the surface, it's really projected. I want them all. I want them all. I don't want them to disappear. I want, instead of these nulls, I want all of these points here, right? So I don't want these ones, but I need all of these ones filled with the proper content, right? How are we going to do that, right? Now, this is a multi-step operations. So we will sort these list, the current projections a few times, step by step, and then eventually reconstruct all the data we need and place it where it's supposed to go, right? The first step will be to take our pattern and the actual output and literally says that everything, all the hexagons, all the components which are all the branches which has nulls, means that not a single point is touching the surface. They're supposed to go away. No nulls, please. No branches, please. Just cut them off. I don't want to deal with those because they are leftovers, right? This is the first step. I'm sorry. So how are we going to do this? Well, that's where the next output of this node will actually help us. If I look here, let me just bring another panel and plug that in and look at this. You will notice that it has numbers. Now, these numbers are the indices of points projected onto, whatever you projected onto geometry, right? If it wasn't able to project, the index will be -1. If it will project, the value will be 0. Right? So we're going to see that for every element here which was null, which is not projected, right, we have a corresponding index -1, -1, -1, -1, all nulls, right? For example, let's look at this one, -1, -1, 0, it was projected, -1, -1, -1. Cool. Awesome. So what we can do with them is we can actually use an expression and get ourselves a Boolean as a result. So basically, we will ask the system, does the every number here in the list is equal to -1? And if it is, says that it's true. If it's not, let's say that it's false. Can we do that? Yes. Expression. And we will literally type x equal -1. Or basically, if x equal to -1, right? We're going to use a gates for that, but here it's just much simpler. So plug that in, right? And it gives me, let's look at this. It gives me the set of booleans. You see, -1 true, -1 true, -1 true, and so on and so forth. So the reason why this expression gives me booleans so easily is because these numbers are, well, basically zeros and ones, and the booleans are always the absolute values. And Grasshopper is smart enough to take this type of data without any conversion and understands that they just by saying which is true and false, give ourselves the list of basically which is equal to -1 or not, it gives me the actual true and false. And the numbers can be different. Maybe it will be the numbers from, I don't know, whatever the numbers can be, like maybe 0 and million gazillion, right? But when I have an expression, it will automatically return me the Boolean state, right? Is it the true statement or it's a false statement, right? But even though that we did this, there is actually an issue. You see, the negative ones now is true and the zeros are false, right? This by default, because our check is equal to -1. So I actually want to quite the opposite, because if it's outside, let it be false, and if it's inside, let it be true. I believe it's much more logical. So what you're going to do is we need to flip our Boolean operations, our Boolean results. How are we going to do it? Through our specification of a primitive type of data. So if I'll plug the Boolean here, it just passes it through, nothing changes. But if I will right click, I have an option to invert. And it inverts. What was true becomes false, what was false becomes true. Very simply. So now the false values are the nulls and the real numbers are the true. Fantastic. Now, what else we need to do? Now, our goal, once again, for this stage, is to eliminate from the data tree only the branches which has all the nulls. We don't want to eliminate this, we want to eliminate only this. Meaning that this set of values will not really help me much, because it is individual for every element. I need one for the whole stack, right? So for example, if there is all nulls, it will be false. If there is at least one of them is element, it will be true for all, right? How are we going to do that? Well, actually multiple ways, but the one I prefer is the mass addition operation. It sets under the math operations mass addition. Oops, sorry, it's the wrong one. Mass addition. I already explained, I believe, what mass addition is. I believe we already used it before. So mass addition is just, well, mass addition with a partial result, right? This one plus 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 this one will be the result, and the partial results are results between them, right? So, and this is another cool property of the Grasshopper, is that when it is a Booleans, basically false and true, or true and false, they automatically related to the numbers, right? 0 and 1. False, 0, 1, true. And Grasshopper understands this, of course, really, really well. So if instead of, if I'll plug the Boolean operations into the mathematical node and ask to sum them up, it will be it will do the operation with numbers, right? So when I said sum, it will take this number, it will take these values and convert them to numbers. 0 plus 0 plus 0 plus 0 plus 0 plus 0 equal 0. This one, same. This one, 0 plus 0 plus 1 plus 0 plus 0 plus 0, 1. This one, 3. This one, 3, and so on and so forth. So I'll plug that in, and I will look at the output. It gives me the list of numbers, right? Corresponding to that, 0 related to all of them, they're false. 0, 0, 1, 3, 3, 3, 3, 0, 1, 6, it just depends, right? So we have a lot of numbers here. What next we can do? We can make another expression. If x equal to 0, right, then it will be true. So expression x, equals 0, x bigger than 0, not equals 0, x bigger than 0. If x is bigger than 0, right, like 1 or 3 or million gazillion, then it will be true. It basically means that there is some true value, meaning there is a value inside, right? So I'll plug that in. Oh, sorry, not from here, from here. I'll plug that in and I'll look here. Now I have, instead of a multiple sets of values, I have one which represents them all. This list of values are false. This list of values are false. This is true. This is true. Why true? Because there are numbers there, right? We already sorted it out. Fantastic. So now I have basically the rule which I can use to take my original list of data and clean it up. Basically split it on the two different sets of data. One set of data, the one we are looking for, is the one which is true, and the one we don't want is the one which is false. Can we do that? Yes, we have a very specific node for that. It sits under the sets lists called dispatch, this one. All right, let me just organize this stuff a little bit, right? So Then put it here, put it here, put it here, here. Let me just kind of hide this like this. Right, dispatch. What dispatch node does, it takes your data structure, and you're going to see that it actually looks for the list. It doesn't mean that you can't plug the data tree with multiple branches. Of course you can and you will. But it basically says that it doesn't really do anything with the branches. Instead, it does with elements inside. And this is exactly what we want. So if we will put this data tree into the list, and our dispatch pattern will be this pattern, it will split it on the two groups. List A is true, list B is false, right? Once again, we're looking for the true. We look for the elements which has at least one element within the branch, right? Let's do that. Plug it into the list, dispatch pattern into the pattern slot, and let's look at the output. Look at this. Interesting. So, as I said, this node works based on it doesn't really take your data structure. It doesn't remove or mess with your tree branches, but it works with elements inside of the list items. And you see what happened. The true basically left us only the elements, right, which are corresponding to the true set, right? The elements which has at least a single value within it, right? And it basically calls out all of the branches, all the list items in these branches which has only nulls. You're going to see they disappear, right? Nothing here, nothing here. Let's look here. Like we have an elements which are full stack, of course. Here we have a list of full stack. And once again, missing. The alternative will be all nulls. You see nulls everywhere. And once again, the branches still intact, they are still there, and meaning that I actually can merge that together. If I use a merge command, I can merge list A and B and get where I started. I don't want that. I need a list A. What's more importantly, I don't even need these empties. I want them to go away. There are no data anymore. Please remove that. Can I ask Grasshopper to remove all of this kind of junk? Yes, I can. For that, I will use the node which I briefly showed previously, very randomly, but never explained. This node called clean tree. It sits under the sets, tree, clean tree. Now this node works on the trees and clean them up from different artifacts or elements. For example, it can remove empties, remove invalids, and remove nulls. If I'll plug this into my data tree, into the input slot, and look at that, you will notice that I actually get quite a shitty result. First of all the elements, all the empty branches are still there, and what's worser, I lost my nulls. And nulls are very important for me because they are placeholders for the content which is missing. They are there, they have their indices, they are crucial for me. I want them to keep for now. And it's completely removed that. But that's because the default values of this node are not necessarily the ones you're looking for. So if I hover on the null, on the remove nulls, it said one locally defined value true. The default value is true. No, please set Boolean false. We want that it will not touch our nulls. What we want instead, it will remove empties, and by default it is set to false. Right click, set Boolean true. Oh, look at that. Fantastic. Now we basically have, if you think about this, just visually, we have literally the same stuff, right? Identical. But the actual structure is not the same. We cleaned up all this mess now. But this, once again, a multi-stage operation. And even though that we cleaned all the ones which are definitely not supposed to be on the geometry, we never sorted it further. What next we supposed to do? Well, let me look at our, oops, sorry, like this one, sorry. Let's hide this, okay. Hide this, let's look at this one once again. So this is our current output, and now we don't have branches with all nulls, right? But what we want to find the elements on these branches which are incomplete, right? Incomplete, and kind of separate them from the ones which are fully assembled. Like for example, all of these ones, they are okay. I don't even want to touch them. I want only these ones. I would like to take all of these edges, all these edged branches with elements within it, with all the nulls, right? And then I will do operations with them specifically. How can I do that? How can I take and basically split my data tree and remove the elements which are completely full, right? Like these ones. Now for that, we will use the node called split tree here. All right. Okay, so first things first, let's one sec. I'm sorry guys, I'm back. So what we're gonna do, we need to somehow take some kind of a tag or element which will describe by the specific property the differences between the elements or the branches which has nulls and the elements which don't, right? How are we gonna do that? I will probably do it this way. I will take our nulls and I will actually figure out the actual positions of the nulls for every given branch. I will basically pick their indices, and when I will do that, it will give me the list of branches which has the elements with indices for the nulls. So basically I will solve two tasks at once. Let me actually show you. So first of all, let me find the amount of elements in every single list. What are the amount of elements in every single list? Well, 6, 6, 6, 6, all 6. Well, we know that. We need to tell it to the system. So we'll use the command called, well, we're going to use statistics, right? Statistics. And we'll use the length, or we will use another node called list length. This one, it's here somewhere. Well, list length, here it is, right? So I will plug our data tree, this one, into the list length, and it'll give me the set of numbers 6, 6, 6, 6, 6, 6, 6. Okay, that's cool. What next I want to do? I would like to create the indices. So I basically want a separate set, a separate data structure, which will contain indices for all the elements. Can I do that? Yes. Series. This is the node which you used before. Starts with 0, step with 1, default values, length is 6. Let's check. It will give me the uniform structure with values 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, and so on and so forth, right? So null 0, null 1, numbers of the point 2, and so on and so forth, one by one, okay? Next, I will use another new node, which we never used, and we will actually, remember I said that nulls are tags, and we can actually operate with them. We can look for them. And if I will look for, go into the list subcategory, and I will take this node called null item, this null item actually, in fact, looks for nulls. So if I'll plug the same data tree, my original one, into the node, and the output, it will give me the null flags in booleans. True, true, nulls, false, not a null. True, true, nulls, false, 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 not a nulls, right? So we basically now know which are of them are nulls and which are of them are not. Okay, what's next? What for, right? What for? Well, now we do a really beautiful operation. We will use this pattern, because this is in a set of pattern, and sort not our original tree, not this one, it will be the buttered butter, but instead we will sort this data tree with indices for all of those, right? And if I will use the same node called dispatch, plug this as my list, we already learned about this node, right? Put it into the dispatch pattern, we have ourselves an output. Let me just bring the output here. And we're looking, the true is A, the B is false. Now true, once again, I remind you, the true are the elements with the nulls, right? So it'll give me the elements with the nulls. Let's look at this. Look at that stuff. Look closer. So what we actually did is we took our series with indices for all our original data tree, and through our null flags, which describes which element is true and which element is false, split this on two groups. The one group will be the data tree which contains indices for the nulls. Look at this. The indice for the null here, right? You see 0, yes, 1, yes, nuh-uh, 3, third, fourth, and fifth. Third, fourth, and fifth. Same here. These ones, no, not even here. Sorry, this one is not even here, but 0, 1, and 5 are here. So basically, they are indices for elements of nulls in this list. And this is very important. But on top of that, we have paths which ideally supposed to contain only the branches which has at least one null inside. Because if it didn't, it will be in the list B, right? I hope that's clear. Now, before we move on, let's actually look at the data structure. That was our original data. This is our indices for the data structure. Look at the paths. We have a problem. They are not the same. So if I really want to use it as my masks for the future, I couldn't, because it's the wrong path. It's supposed to be the same. What's the problem? Well, some of the nodes add additional number to the path as a part of its data management. And which node was that? This one. It's this node which does this. So now we have a conundrum. Not a conundrum, actually. We have a problem. So this serious node gives us the paths of with 4 elements. The original one, the proper one, has only 3. And in the dispatch node output will give us in the end 4, the biggest one. Why? Well, because that's another situation which I want to mention, that this node has data matching based on the longest list built in. Yes, that's yet another node. But that's a good thing, because it matches the values based on the longest list. If we change this list of data and make it shorter, like for example, we don't really need to do something with the complex with the paths. We just make it shorter than this one. This one 3, this one 4. What we need to do, look at this, 0, 0, 0, 0, 0, 0, 0, they're all 0, 0. So if I will simplify that, you just chop them off. It will be 2 elements, and this one will be 3 elements. This one will go through, right? Right click, simplify. Look at the output. Now we're taking it from this list, right? Fantastic. And it's just a one-click operation, basically, right? Always be careful about your data structure. If you need to weave different lists and data structures together, one from the one, another one from another, make sure your paths are proper paths, right? So be aware of this, right? Mentioned before, I say it again. So eventually what we get in return, let me just kind of organize this a little bit, right? So what we get in return, once again, so we will get ourselves a list of, that's not cleaned yet, but a list of indices which represents the nulls, the actual elements which are missing, represents nulls, their current positions, and on top of that, it represents the paths for them, right? So as you're going to see here, there are no branches, or they are empty, which actually has all of the elements filled in, right? Because remember, we are looking for the null flags, right? And if the branch doesn't have any, right, because it's completely filled, it's somewhere there, it just basically filter it, right? It's in the B slot, right? So basically that now we have this amazing, when very important for us, data structure, or the data tree, which consists with the proper indices for the nulls. It has the proper paths, and it has only that amount of paths, not for now, but very quickly, which actually only affect or refer to the branches which has nulls inside, right? So of course we need to clean it up. So let's go clean. Right now we plug it into the tree, remove empties. We don't really care about the nulls. There are no nulls. So set Boolean true, plug that in, bam. Okay, fantastic. I even just kind of call it a name. I will call it paths, right? We will use it. We will use it multiple times. All right. So now we're gonna take our original data, which is this one. This is our, let me just kind of hide this one now. Let's take this one. This is our current projected points, which we already sorted from the branches, which completely misses the surface, right? And we need to sort it once again, and we will remove, basically split these on two parts once again. One is the outskirts, which has missing elements, and the one which completely assembled, right? So I'll take this stuff, put it into the data, and our mask will be what? The paths. So statistics, take the paths. Or maybe like this. Maybe it's like this, right? Take the paths, put it here, click. Now, by default, if the node has one or more output, it can visualize only the first one, not the second one, right? It depends on the node. For now, what I'm going to do is I will just change the outputs. This one will be trim, right? And this one will be, I don't know, full, whatever. Hide this and use the data node just to pass data through and turn it on separately, okay? Look at this. This is all our edges, which indeed have missing elements. Here they are. And that's, by the way, the paths for them, right? Fantastic. And that's are the full elements. Here they are. Everything is here, right? Like everything which is fully assembled, right? You can see these points are not connected, right? And overlapping elements are not here as well. Cool. So now when we did that, we actually ready to work with and find the lost elements in the original pattern which we created, right? The pattern on the big surface here, it definitely has these elements. I want them back, so I want to select them first. I want to find them. So let me look at the trim again and look at the values, right? So we need to find all of these nulls in the original big data tree, and then we will do some modifications with them, right? So how are we going to do that? Well, we have our original points. Let me actually kind of do it like this and bring them closer to me, as well as the vectors, right? Like this. Let me maybe push the, how much I need to push it down? Like this, right? Okay, something like this. We will organize everything a little bit later. So this is my points, my original points. Once again, toss it to the data to figure it out. Here they are. So I need to find the branches, which consists the groups of hexagons, which are related to these ones. Can I do that? Of course I can. I already have the paths, right? So this is basically the paths of the branches which are contains nulls, right? So what I'm gonna do is I will use the node called tree branch, right? Where is the tree branch? Here it is. I hope you remember this node. The tree branch picks the specific set of branches with all the elements within based on the paths. So we need to give them the specific paths we need to pick. Which ones of those? Well, these ones, right? These ones. This is the paths. And because we already have these paths here, right? We're going to use them to split our pattern. We already have that here. I could just plug it from here and put it into the path. And the tree will be our points. Let's look at this. Fantastic, here they are. You see? These are all the original branches with points which are referred to the ones which are missing. Cool. Now, before we do something with them, let's actually do the same operations with vectors. I will remind you that these points are not in the proper spots. They are up. And we already have projected one, so they will go down. On how much, we'll figure out later. For now, I need the proper directions for those, right? For that, I need to pick the proper vectors. Not all the vectors, but only the vectors related to these points. How are we going to do it? Well, the same way. This is my vectors, right? Oh my God. 1 second. Vector. Okay, cool. So we will do the same. It's just this data tree, and that will be our vectors. Let me visualize that they are indeed they. So this is the anchor, this is the vector. Here they are, right? Okay, proper orientations, the proper vectors, we need them. Cool. Right. So now we have the proper set from the original pattern. Now we need within these branches find the proper elements, because right now, as you can see, these elements and these elements are overlapping, right? So these ones I don't really want to touch, they're already here. These ones which were nulls in the original data tree, right? So I need these, not this. How are we gonna do that? Using a list item, of course. So I use a list item, right? What is my list of data? These branches, right? What are the indices for the nulls? We already know. Here they are. That is my paths and that are my indices. We already figured it out when you did all of this stuff. So I'm gonna just take these paths. Remember, every single one of them is an indice for the null in this data tree. But they are identical to these ones as well. Same paths, same orientation, and same order. So they, of course, will work. So I'll plug them into the index, click, and here they are. Look at this. This is all our missing points. Fantastic. Now we need to do the same for vectors. So what I'm going to do, Ctrl-C, Ctrl-V, and actually there is a one important note here. You can see when I am copying and pasting, instead of the output item, it will change it to I. And they're different now. And it just bugging me, so I'll just duplicate it like this instead, right? Delete this one. Right, let's plug that in here. Okay, so now we have the proper points and their proper correspondent vectors, right? Now we can move, finally. So, but that's the question. On how much? Now, direction, we know. We already have our proper vectors and proper points. We need to move that down. But on what distance, right? Well, we actually don't know. How we know? There are no surface, right? How I can even calculate where it's supposed to be, right? The Grasshopper couldn't because there's no surface. How I supposed to know? Well, I don't. But remember, this is an approximation projection approach. We don't know, but we can predict. And we can predict it based on the data we already have. Look at this. We have ourselves, let me just hide this, hide this, hide this. We have ourselves a pool of these points, the full ones, right? They definitely, by default, using our standard projection, already fit the surface. And that means that for them, there is a counterpart on our original points, right? Which are corresponded to them, right? Because it takes them and then project them, right? So they are the pairs. So if I will take only the pairs for these points in the original grid, for these green ones, in the red ones, right? Which are sitting on top, I can calculate per each a distance between the pairs, like distance between them, distance, 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 find all the distances corresponding to each other and take an average of them. And that will be the average distance for us to move the points. Is it ideal? No, it's not. Depends on the curvature. One part of that can be very much bent, another one is not, and it will not compensate it. So what? Not a big deal. We don't need to be exact. We need to be in a relative proximity. So this is good enough for us, and we will do that. How are we going to do it? We need to first take the pairs for these full projection ones. How are we going to do it? Using the statistics node again. We will take the paths, right? Once again, the paths are identical. We take the paths of those, right? And then we use the tree branch again and take from the bigger pool of our original points, right? So let's do that. I will go in, use statistics node. Let me actually call it full, and this one, let's call it trim. Let's try organizing things a little bit along the way. So I will take the full, put it into the tree paths. This is the paths which I'm looking for, right? I need to find their origins in the original grid. This is my original points, right? This goes right, like from the original point, right? So let me hide them. And I will use the node called tree branch again, tree branch again. This is my points. This is my paths. And of course, we need to move that and organize in a second, right? Here they are. So that was our pairs, right? What are we going to do next? We will calculate the distance. How we calculate the distance between the two? A few ways. First of all, I can construct a vector through 2 points, or I can just calculate the distances because these are primitive type of data. So if I will go to the vectors, points, I can find here a distance command. Let's plug that in. Point A, point B. Which one is which? Which one is first? Which one is second? It's not important, right? So this is the point A. Let's plug it in right there. This is the point B. Let's plug it in right there. Let's look at the distance, and it gives me this pool of distances. So every single one of them has its own. So what are we going to do? We need to find average across all of them, not within their branches. So flatten the tree. Right click, flatten, and average. Right? Plug that in. Look at the output. We get ourselves a number 4.010425. That's the average distance, and this one will be used as a single value for our to move our points down. So before we organize everything here, I know that's it's a spaghetti code. Let me actually do the projection, and then we organize things a little bit before we move on. Okay, so projection is a movement. So we can't project, once again, we can't project, nothing to project, but we can move. So we know in what direction. This is our vectors. So we'll take these vectors, we'll take these points, and we will move on this distance. What node can we use for that? Well, we actually use a few different modes. There are different ways of doing that, but the most common one and useful one here will be the one called move from the Euclidean transformation tab. In the transform, Euclidean, here is our move. I believe I briefly used that, but never explained. It's very simple. We have our geometry. This is our geometry. It can be anything, not on the point. It can be whatever you want. And the motion is a vector. You're going to see it is a vector. Hovering, motion, it's asked me for the vector. We have the vectors. Here are the vectors. But if I plug them in directly, you're going to see that we moved, but very little on one unit, because this vector was a normal vector, right? 1 unit. I don't want it to move on a 1 unit. I need to move it on 4 units, right? How are we gonna do that? Well, I'm gonna take my vector and multiply that on my my amplitude, or I will use a specific node for that called amplitude. Here it is. It locates under the vector amplitude. This one. Plug the vector, plug our amplitude, plug the motion. Here we go. Look at this. It's now in the proper position. So this is the one part, the missing part, and this was the original part, which we have here. Oh, sorry, not this one, this one. This one, right? These parts. Let me actually hide the, where is my, yeah, here, okay. So that was my incomplete part, which was projected, and this is its counterpart, right? Here they are together. Of course, we need to merge them together. We will do it in a second. So before that, let me organize this stuff a little bit, because this is horrible, right? First of all, let me take this and push it down a bit, right? Something like that. Let's align this. Let's maybe I put it down here, right? Why not? And these ones are actually, okay. So let me just take then these things, put it down like this, okay? So this one is a big problem, right? So let me just kind of put it down, put it to the left, this one a little bit to the left, something like that. This is my statistics. Now let's put it down here like that, and let me do it like this and like this. Yes, okay, that's better. Maybe like this. Which one is better? I don't know. Nah, probably not. Let's do it like this. And we're probably gonna take another one. Right, something like this. Let me now align these ones a little bit more. Okay, what else can I do? I really hate this zigzag line, so I need to do I need to kind of like move it to the right. Everything's supposed to move to the right somewhere here, right? Something like this. I mean, not ideal, but I believe a little bit better. Let's move it to the right. Let's take this one, push it up. Maybe like this. Okay, that's a little bit better. Let's keep it like this and just keep moving, right? Okay, so that's our new set, but it's separate, right? So these values, they are our partial elements which are projected, are separate. In this branch, it still has nulls, remind you, and this one is the original ones which were projected separately here. We need to join them together. But if I'll use just a merge command, what will happen is that all the nulls will be persistent and I will lose the order of points. I want that these elements, right, which are now in the shortened list 0, 1, 2, 3, 0, 1, 2, 0, they already lost their positions, right, when we actually sort them out. But the original data is still knows where the nulls are, and of course I still know what the indices are for the nulls, right? And this is everything I need to do, because now what I want is I would like to take these elements, right, from this tree and replace the corresponding nulls, right, these ones. And for that, I'm going to use the node called the replace item. So I will type replace item. Now this node locates under the sets, lists. Once again, if you don't know, once again, Control Alt left click. I mentioned multiple times. Here it is, right? List. Oh, replace items. Here it is. Now it looks for the list, and this is our original list of data. The item is the items we want to replace with. So this is these elements. And the indices of an elements we want to replace. What are the elements we want to replace? We want to replace nulls. What are the indices for these nulls? Well, here they are. So let's plug that in. Indices. Click. Amazing. It now works. However, if I'll check, you remember the actual construction. Free elements describes the path. Here, for. Why? This node adds additional history and additional complexity to the path. What we need, remove it. But if I will take and simplify this, it will remove all 2 zeros. And this is crucial for me. I don't want it. The original free paths were free numbers for the paths were very important for me, because I will remind you that we are not only working with the hexagons, but we're working also with triangles and quads. So the original data structure is really important for me. I want to keep it. How are we going to do it? How I can remove only the last element? Well, it's actually a pretty common operation, and we have a dedicated node for that. So in the sets tree, look for the node called shift path. Where is this? Here it is. Shift paths. You plug the data in all your tree and looks for the paths, and it will call one of the elements. By default, it's set to -1, means it takes the last one. You can make the first one, and the amount of offset basically describes how many elements you want to call. So plug that in by default, and bam, here we go. Now we have a proper data structure. Let's actually check that it is a proper data structure, shall we? So I will go in and I will construct a polyline and plug that in. Let's go, set Boolean true. Fantastic. Everything works now. Perfect. Well, now let me quickly organize this, and then we will move on, because this one is separate and our original full blocks here are separate. Oh, sorry, wrong node. Is separate. We need to merge them together, of course. So before that, let me organize it yet again, because I hate this. Let me just go straight through like this. Okay, well let's do this. Let's do this. I believe that will be better. So this one goes right there, like this. And this one supposed to go right here, because this one will be in the way of this one. Yes, so we will do this like this. Yeah. Okay, cool. And move this one to the right. Let's look at this one, supposed to be higher up. Or we'll just take all of that and put it down. Oh, sorry, not this one. My God. All right, okay, that's better. So now let's go back to our task. What we need to do, we need to merge. So these ones with the original full ones. How we're gonna do it? We just use the merge command, right? Why I'm doing it with the merge command? Because the overall data structure gives me a possibility to do so. Here for the full, we have the proper data structure only for the inner elements, and these ones from the same data structure but for the outer elements, right? So the paths will not intersect. One goes after another. We didn't really change the data structure, so we can easily merge it, and the order will not matter because the paths has already the proper order. And here we go. So if I will hide this one, let me just do it like this. Right. Let me actually prove you that the order here is correct. Actually visible by the paths, but let me just show you, remind you that a few lessons ago we actually constructed ourselves the specific a cluster which I said we will be using for debugging. Well, this is a good example for that. If I will use the polyline, oh, here it is, polyline, and turn it on, you're going to see that everything here, everything correct, but is the order correct? Let's use our cluster. For me, it's called the tree branch. Oh, branch slider, sorry. Branch slider. Oh my God. Here it is. Yours probably called differently, I don't know. So we will take our polylines and let's get, I don't know, 100 elements. Let's take a look. I'm sorry, connect. Okay, this is the first one. Here, green one. Let's go. Oh no, it's like this. Where is the top view? Oh yeah, the surface was flipped, of course. So you're gonna see root, column, column, column. Perfect. It's ordered perfectly. You're gonna see how it just switches one after another, row by row. Amazing. Cool. All right, this tab works. Pretty happy with that. What's next? Now let me actually do one more thing before we end this session, and that will be an option for us. So, you know, right now we have this kind of additional elements, right, on our on our pattern. Let me actually hide the original surface now. We don't really need this, right? So this is our BREP only. We don't need this as well. So we already created these additional leftovers, right? So they will cover all the parts. But what if you don't want that, right? What if you want it to be trimmed? Well, let's give ourselves an option. It's not really very beneficial, but sometimes it can, so why not to bring it in? On top of that, it's very simple. But before that, I completely forgot. We are working with points, right? So they are points. But we don't want points, actually. We want planes, right? So they are points. Look at this. This is all points. All of that are points. We want planes instead of points. So we oriented our points or placed our points, do all the data management. And now it is time to actually go in, take our planes, the original ones, these ones, and actually orient them onto the points, right? So let's go in and I will use the notch for the planes. I'll call them planes, right? Like this, where it's supposed to go. Somewhere here, right? Okay, so they are my planes. So how I map the planes? Well, first of all, I need to sort them out, right? Because here we have a lot of planes, right? But here we have a very limited amount of points. What we need to do? Well, once again, data structure is identical. So I will take the statistics node, I will take my paths, right? Which are the paths for these points. And I will use the branch slider, or tree branch, sorry. And I will use this node to specify what kind of a planes I want, right? I want the planes on these paths. Here they are, right? We already did it multiple times before, so I hope you totally understand the process, right? So here they are. So when we have them, but it's good that we have them, but we actually don't need them here, right? We need them where the points are. We did all this stuff to make it happen. And like, oh my God, now we need to do it again, right? No, of course not. As we already have the proper positions, the proper orientation, and the proper data structure, the only thing left is just place them there. And there is a couple of ways of doing that, but the simplest one is the one we used before. We used the node called orient, and we will use our geometry as our base, which will be our planes. We need to find the source or the pivot of the geometry, which will be its origin, and the target will be our points, right? So you're going to see here that it takes it as a whole. So I can't specify geometry and the source at the same time. I need to specify geometry and I need to specify the origin separately. For that, I already showed it. We use the node called deconstruct plane. So we use the node called deconstruct plane. The plane, this is our origin, right? So the geometry will be our planes. The source will be by default its origin, and the target will be our points. Bam. Here it is. Now it's mapped, or placed, or oriented on the proper positions. Fantastic. So let me align it a little bit. Oh my God, how am I gonna do this? The most challenging part is just like trying to align everything. I don't know, let's do something like this. Oh my God. Okay, never mind. Yeah. Oh yeah, that's a disaster. Okay, never mind. So let me just kind of take this, put it down here. Okay, good enough, good enough. So now we have our planes. This is the actual proper content which we're looking for. And once again, they are indeed the planes, the axis, and the points at the same time. We're going to deconstruct these planes, right? You know, once again, they are planes, so we're going to deconstruct the plane again. And we get ourselves the origins, we get ourselves axis, everything which we want, right? So we didn't lose anything, we actually add. Now, last but not least, as I said, we want to have ourselves, to give ourselves an option to, when we already mapped everything, remove additional rows or additional overflows if we don't want them. If we add them, right, we add them here and like, you know, I don't want to remove them. I want to remove everything, even if it's overflows and touches somewhere. I just remove it. Remove everything which is overflows. Give me only the full hexagons by default. Can we do it? Of course. So I will use the value. Excuse me. I will use the value list. And my bad, sorry guys. And I will use the let me define the name. Well, I don't know. Let's say fill. Or I just don't even know how to call it. And inside it will be a trim. and a fill. So 0 and 1, right? Or maybe vice versa, let me think. And now it's probably like this. Okay, but still need to change the name for that because fill is not nice. How we call it? I don't know, completion. I don't know how to call it really. It's up to you. Call it whatever you want. So so we have a value list. Now we need to have a filter, right? This is something which we did before multiple times. So, oh no, it's the wrong one. We did it multiple times before. This will be our gate, 0 and 1. Here, trim will be 0 and the fill will be 1. So this is the fill for sure, right? What's about the trim? So if we want to eliminate all of those, right, what we need to do, we need to take our... Oh my God, no, I messed it up. Oh, no, wait, 1 sec. Okay, yeah, that's better. No, we need to fix it as up. All right, yeah, that's better. So what we need to go is we need to, what we need to do is we need to take our elements which are inside, right? These ones. Oh, sorry, what I'm doing. These ones. And take their paths, right? And then sort all the current points using my paths from these, right? I believe that makes sense. So let's do that. Go here. Okay, so I will use the node called statistics, take the paths. This is my paths. Now I will use the branch, tree branch as well, as we did before, multiple times already. Tree branch, we'll take our geometry and our paths and plug that in right there. Okay, so now based on our solution, our options, we're going to switch it between trim to fill. Trim. Let me just kind of hide all the unnecessary elements here, right? So this is trim. It's all to the edges. Let me construct the polylines. Here they are. Oh my God. Like this, right? Fantastic. And we still have some points somewhere. Come on. Where are they? Yeah. Go away. So this is our trimmed version, right? As you can see, we have all of these leftovers, but we're gonna trimming it, right? Like this. Fantastic. And this will be our fill when it just fills through. Okay, cool. That's great. Now, I would like to mention that if let me show you a couple options. So if you not specify the additional elements first, so let me just go in back to the trim, for example, right? And if I will go in and remove all the additional elements by default, it's reconstruct itself, obviously, because we don't have these additional elements which it need to compensate, but it's not breaking. So everything works as intended. I can add more, right? It will me reorient that because it, once again, it sorts them out here, but the overall structure keeps being the same. One note I need to mention is that on top of that is that if we will switch to fill, right? And now we have these additional rows, and we have these additional rows because by default our pattern was anisotropic, right? So it was longer and falling off the surface, just originally, right? Even though that I don't have any additional points, right? Our original pattern, let me just kind of turn it on again. Our original pattern exceeds in one direction, not in the one which we added our additional columns in the beginning, right? When I add like 6, right? 3 to the left and to the right. But by default, it's just longer, right? But if this is by default longer and we are in the anisotropic mode, then when we set the the option, our switch to fill, it will try to fill, but because there's nothing to fill here, we didn't really add any additions in this one, it will fill only in direction when it's overflows, right? If nothing is overflows, the fill will not work, it will not add anything because there is nothing to add, right? Oh, I believe that's clear. Right, now before we end this, let's actually check how our additional geometry works, right? Isn't that interesting? We did it quite a long time ago, but tested it on only a single surface, not on the multi-surface. We did some modifications. Will it work? Of course it will work, but in a little bit different manner. So let me just go in and bring 6 back here as it was. I will go back and turn the fill back in. And now I will do a switch. I will go and switch this, for example, to, let's say, triangles, right? Now, it looks as intended. It works nice. You don't see any issues because there are no any issues. However, if you switch to quads, an interesting thing happened. Look at these kind of peaks here on the sides. Now, it's not really breaking anything, right? It just looks interesting. You may say that this is an error. Probably it's not supposed to be like that. Where is the, last part here, right? Or where is the last part here? That's the full hexagon, isn't it? But the answer is no, because originally when we switch the mode, where was it once again? I need to highlight it for sure in the future lessons. So when we switch the structure, right, we actually changes the amount of elements in the list. That's why I said we really, although these three numbers in the path are really important because they work across all of those, right? But the hexagons is bigger. It works with 6 points. The quads works with 4 points, 4 by 4, and all the scripts figuring out which one of the element is inside, and then if some of them is on the surface, not inside, on the surface, it finds correspondent, but there are less amount of correspondent points. So when you switch the different mode to the triangles and quads, it works individually on all of them, not on hexagons anymore. And because of that, for example, this quad, right, it's just touching here, like everything else is kind of falling off, but it's still keeping it, right, picking it. That's why you have this kind of like a star form, right, or something. Just FYI. So it works as intended, and it works really nice. Now, last but not least, I probably want to mention the order, just in case. So the order of a hexagons and the order of a triangle is a little bit different from the order of the the order of quads and the order of triangles is a little bit different the order of hexagons, if you remember. So if I will use the node our branch slider again, branch slider again, and you're gonna see that it works like in this kind of circular motion, right? And then the next one, then the next one, the next one. You see, it's doing this stuff. Once again, just if you forgot. And last but not least, not last and last for the next lesson, I would like to mention the planes themselves. So we now constructed ourselves a planes, and we oriented the planes, but, and this is very important, but which I need to mention, the planes themselves, they oriented not based on the BREP. They are oriented based on our original surface, right? This one. And if the surface is different, the positions will be correct. Don't worry, it will be the proper positions. But the actual orientation, inclination will be taken from the original one, because we take it from the original one and place them on the normals to the BREP, right? So their actual orientation inherits the directions and inclination of the original one. In some situations, it may be a big problem. For this branch of the script, which we already do, this is totally fine. Now, I, of course, can go in and realign that, and I will in the next lessons, but not for this branch, because here we have a lot of leftovers. And if I will change the inclinations for ones, and will not be able to change the inclinations for another ones, because I definitely don't know where it's supposed to be. I can't predict this, and I can't even simplify this as the standard distances. I prefer to keep it uniform, right? But in the next session, we actually do a second branch, and we will not only align the planes, we'll remove all the overflows, we remove all the duplicates, because the second mode, right now, basically, we actually weave ourselves a hexagons. But what if you don't want to weave a hexagon? What if you want to use them as a placement for geometry? There is a lot of overlaps. There is a lot of points overlapping, sitting on top of each other. We need to solve that. And that will be the second mode. Everything will be aligned on our BREPs, and all the duplicates will be gone. But that will be in the next lesson. All right. Did I mention everything for this or not? What next should I mention? Oh yeah, you're gonna see there is a hole here, right? But you're gonna see it's actually not a problem for the hexagons at all. It just passes through and projects everything it need be on the proper positions, right? What if you want to have the hole, right? What if you don't want that your elements will be inside? Well, it actually will not be, because we will eventually bool this out. It doesn't matter if there is something in here, but because we have on top of that a trimming operations, you're going to see it will not even go here, right? So it's basically right now this patch was kind of left alone. You don't have a construction of a quads, because of, for example, when the quads, they are actually not kind of connected to, they go through the hole, right? So that's what I want to say. Anyway, guys, thank you very much for watching, and yeah, I will see you in the next one.